You will probably get a permission to record.
Yeah.
Mhm. Hi, Jules.
Hello.
How's it
Hey.
going?
All right.
Mhm.
Yep.
I think, Paulo, we should also remind people, if people are not getting our announcements directly, please just send us your email and we will add you to the mailing list so that you get it firsthand and not
Yep.
don't have to rely on anyone
Yep.
for the announcements. So we will wait another minute. We usually start a couple of minutes after the hour.
Sure.
Paulo, maybe we should get started, right?
Yeah. We
Okay, I
we
think
got
we
a
get
fair number
started.
already. So
Yes, and apologies for scheduling this on a holiday in Europe. But the good thing is that we are recording these and we have a YouTube channel, and so hopefully people will be able to access this. So let me start by welcoming everyone, and it's a great pleasure to introduce our speaker today, Dr. Enrico Peretti. He's currently a researcher at the Université Paris Cité in astroparticle and cosmology. Enrico got his master's degree in physics at Trieste and his PhD at the Gran Sasso Science Institute, L'Aquila. He was then a postdoc at the Niels Bohr Institute in Copenhagen, and he's currently now at the University Paris. I believe, Enrico, you also received a Marie Curie grant, right?
Yeah.
For exploring the astrophysical sources with high energy cosmic messengers. As you know, this is pretty prestigious. Enrico's research interests include the study of galactic bubbles of starburst galaxies, galactic diffuse neutrino emission, study of cosmic ray-induced ionization rates, non-thermal emission from nuclei of starburst galaxies, and many other topics. And he's mostly working in theory and phenomenology, but he's also involved as an associate member with CTA, with ASTRI, the mini array, MAGIC, and as well as LASSO collaborations. Today, Enrico will talk about particle acceleration, propagation, and radiation in starburst galaxies. So welcome, and in 2 weeks, please join us again. Oleg Kargalsiev will be talking. And again, I just wanted to mention that if you're not getting our mailings directly, please just put your email in the chat, send it to me or Jonathan or Paulo or any of the co-chairs, and we'd be glad to add you to our mailing list. So Enrico, please get started. And want to share
Okay.
the screen one more time?
Yes. So first of all, thank you very much for having me here. So it's a great pleasure to give this presentation. So now let me try to hide as much as I can. This that keeps appearing. Okay. And also this one. Okay. So yeah, thanks again for having me. So I will, as said, I will talk about the Starburst Galaxies. So let me first begin by saying what a starburst is. So this is I would say, an iconic image of the most nearby and perhaps well-known starburst galaxy. This is M82, located at 3.5 megaparsec from us. So these galaxies are extremely interesting since they are quite peculiar and different from our Milky Ways. So first of all, as their name says, they are characterized by an extreme rate of star formation that is typically localized in a compact region of a sub-kiloparsec scale or so. And here the star forming activity can be tens up to 1,000 times higher compared to our own galaxy. Then a second thing you can notice from this image of Hubble and HST, and JWST, is the presence of a lot of gas and dust. This, for instance, these red clouds, and this is quite peculiar of starburst galaxies in that gas and dust are the seed of star formation. So we expect a lot of gas to be there, and it's interesting because this gas can act as a target for cosmic ray accelerated at the many supernovae expecting these objects. So in addition, you can also notice this gigantic kiloparsec scaled lobes. These are winds that are powered by the star forming activity taking place in the nucleus. So there are several sites of interest in these objects. So to summarize, starburst has their galactic disk, typically the starburst nuclear region, and the kiloparsec scale wind. So now it's good to provide again some motivation on why it's relevant to study starbursts from the high energy astrophysics and astroparticle point of view. So let's start from the basics. We have the star formation, and connected to the star formation, we have supernovae exploding. So, and as you probably all know, supernovae develop shocks where particles can be accelerated through diffusive shock acceleration. So second, as I was mentioning, the star forming activity is also powering these very fast and massive outflows, which in turns they also develop shocks where particles can be further accelerated or possibly reaccelerated. And so we have a second region of interest for high energy particles. And that was, as I was anticipating, we have a lot of gas and dust, and also a lot of starlight that is emitted and also reprocessed by the dust in infrared. So we have a lot of target material where particles can collide, and so that starburst could possibly behave as cosmic calorimeter, namely environment where cosmic rays are accelerated and they interact before being able to escape. And this is extremely interesting if we think about the implications of high energy particles acceleration, so that we can expect a lot of non-thermal radiation and neutrinos. Okay, so a second good reason to study these objects is that there are a lot of star-forming galaxies in the universe. And if we go in the past, so here I'm showing the star formation rate density, namely star formation rate in solar masses per year per unit moving volume, and here is the redshift. And as you can see, if we move from present time back to redshift between 1 and 2, we see that the star formation increases about 1 order of magnitude. So we expect a lot of radiation coming from distant galaxies, so that we might expect a compound emission as a diffuse flux. Okay, so to summarize, starbursts are interesting for us because there are a lot of acceleration sites there, for instance, in the starburst nuclear region through stellar winds and supernovae explosions. Then we have the kiloparsec scale winds, and we expect a lot of interaction and possibly calorimetry due to the high gas density. And finally, given the large number of galaxies through the history of our cosmos, we expect them also to possibly contribute to the diffuse flux of gamma rays, neutrino, and possibly cosmic rays. Okay, so after this brief introduction, this is the outline of what I'm willing to talk about today. So I will be first starting with some observational facts, then I will talk a bit about transport and multi-messenger implication in starburst nuclei. Later I will discuss about starburst winds, and I finally will conclude discussing multi-messenger implications about the diffuse flux. Okay, so this is an optical view of the M82 galaxy as seen by Hubble Space Telescope. Now, zooming in, we see that the medium is quite different from the interstellar medium of our galaxy. So we have a lot of clouds of different densities and size, and we have a lot also of young massive stellar clusters, all located in this compact region of the starburst nucleus. And this star-forming region and these clouds are all buffeted by a hot and ionized medium. And so here, differently from our galaxy, the warm ionized medium is expected to be subdominant compared to the clouds and hot ionized. So as far as, and of course, feel free to interrupt me if you have questions. I don't know what's your habit, if you wait for the end, or but if you have curiosity, I don't mind stopping anytime. So we currently observe a dozen or so of starburst galaxies and star-forming galaxies in gamma rays, and we observe them with a slope in energy of the order of 2.2, 2.3. And the two most nearby galaxies, the famous M82 and the NGC 253, are also observed at TV energy. This is because they are within less than 4 megaparsec from us. Interestingly, the most distant starburst we are detecting in gamma rays is ARP 220, which is at 77 megaparsec from us. So let's say that we are observing the extreme star formation in the bubble of roughly 100 megaparsec radius. Okay, so I mentioned gamma rays. What about neutrinos? So so far there is no detection of starburst galaxies in the neutrino channel, and this is because they are not particularly luminous. They are indeed dim gamma ray sources compared to blazars or other very powerful extragalactic sources. Nevertheless, I put here a sort of red flag because, as you might have heard, recently IceCube published a 4-point-something sigma hint of a neutrino signal from NGC 1068, but I put it with the flag here because as we can discuss later if we have time and we are interested, this neutrino emission is unlikely linked to the starburst, but more to the central supermassive black hole. Okay, so a second very interesting observational fact about starburst galaxies is that they are lying on a relatively tight correlation that is linking their star formation rate or far infrared luminosity, which is the typical tracer of the star formation rate, and the non-thermal luminosity, both in gamma ray and radio. And qualitatively, we understand this correlation with this sort of cause-effect link. So we have first the star formation and acceleration sites like stellar winds or supernovae. They are more or less directly scaling with the star formation rate, and cosmic rays are injected by these guys, and the interaction of the cosmic ray themselves is then responsible for the non-thermal radiation. So this is the qualitative explanation of this correlation, and we will see it somehow in better details in the next slides. So what about the diffuse flux? So here I'm showing the multi-messenger particle diffuse flux from the cosmos. Here is the energy flux of particle. Here is the energy. And here is the cosmic ray spectrum with the knee and the ankle. Here we have leptons and photons. What I'm interested in the context of starburst is whether they can provide a contribution to the isotropic gamma ray background and the neutrino background measured by Fermi-lat and IceCube. And also I'm interested in exploring whether they can be responsible for a contamination to some extent of the cosmic ray spectrum between the knee and the ankle, where we believe the transition from galactic to extragalactic cosmic rays taking place. Last but not least, so from the Pierre Observatory, a sample of nearby starburst galaxy is correlating well somehow with the arrival direction of the highest energy particles. So it's currently an indication at 4 point some sigmas. So it's not full-fledged yet, but it's interesting to ask ourselves whether starburst galaxy can be actually connected to ultra energy, and I will touch this topic at the end of the talk. So now I'll move to the transport in starburst nuclei. So first of all, let me remind you, starburst nuclei are the most active parts of starburst galaxies, where most of the star formation is taking place. Their size is roughly a few hundred parsec up to kiloparsec. And we can sketch the interstellar medium as a hot ionized medium bathing clouds of different densities, star-forming regions, and acceleration sites like supernovae, for instance. And here, cosmic rays can be accelerated and eventually diffuse away from the galaxy, or they might be advected in chimneys and outflows outside from the starburst nuclear region and then the disk, or they can interact and in the case of proton produce gamma rays to neutral pion decay and neutrinos and secondary electrons and positrons through charged pion decay. So this is why they are very interesting from the multi-messenger point of view. Okay, now for this typical set of parameters of density, magnetic field, and wind and radiation energy density, that these parameters are typical of galaxies like M82 and NGC 253, the most nearby we have. So here I'm showing the typical timescales of electrons and protons in the starburst nuclear environment. Here I'm showing the black curves are the energy loss rate, the energy loss timescales. The green dotted lines are the advection time, while the blue and red lines are diffusion timescale computed in the context of a quasi-linear theory, where the blue line is Kolmogorov diffusion, while red is Bohm. So interestingly, first focusing on electrons, we see that the black line, namely the energy loss timescale, is always smaller than the others. This means that electrons and positrons are well confined in starburst nuclei, or if you want, that starburst nuclei are good electron calorimeters. Regarding protons, here you can see that at low energy we are again in a calorimetric scenario where here ionization losses are very efficient, while here at high energy, even though diffusion is subdominant, we see that there is a very tight competition between energy losses in black and the advection in green. This is why somehow it's difficult to conclude in general whether starbursts are good or weak proton calorimeters. Nevertheless, notice that these timescales are basically practically energy independent, and this means that cosmic rays during their transport are expected not to change their slope and to maintain somehow the slope of injection. So we can model the transport in this environment under the assumption that cosmic ray explore all the interstellar medium phases. So we take the one zone leaky box approximation, where we compute the phase space density of cosmic ray through balancing the injection rate with the escape rate through diffusion and advection and the energy loss rate. And we get the following results. So this is the particle spectra, and this is the associated multi-wavelength spectral energy distribution. Now, let me try to disentangle these plots. So first of all, let's focus on protons. So as I was mentioning in the previous slide, here you see that diffusion is always subdominant, so that we expect a hard proton spectrum, and this is reflected into the pion bump, this black curve here, that is also suggesting that starbursts are hadronic sources, namely from GV energy, the pion bump is the dominating gamma ray component. And so here in black and red, we have respectively primary and secondary electrons, where primary I computed assuming the same ratio as in our galaxy, namely proton over electrons equal 50. And while secondary are produced together with the neutral pions that is giving the gamma ray. So, and notice how the secondary electron curve at GV energies is becoming dominant compared to primaries. And this is one of the reasons that explains the slope that we observe in the radio to mass loss luminosity radio to mass loss star formation rate, correlation. So as you can see here, in the low star formation rate range, we have this dashed green, dark green curve, which is the synchrotron from primary electrons, while at high star formation rate, the dominant one is the synchrotron from secondary electrons. So we need secondaries to become dominant and therefore starbursts to become somehow more and more calorimetric the higher the star formation rate. Now, going back to the spectral energy distribution, here in the multi-TV range, you see that there is a cutoff. This is not due to the maximum energy of protons, but is due instead to the gamma-gamma absorption on the strong far infrared field that is associated to the star formation. And this energy is not lost, but is reprocessed here in this blue curve, which is the electron-positron pairs that are produced via gamma-gamma absorption, and here they are as abundant as secondaries. And these guys, together with the secondary electron, are producing a quite strong synchrotron emission in the KeV band that, if detected, could be used as a smoking gun for good confinement and subsequent absorption of protons and associated photons in this environment. Okay, so we applied this model for
sorry,
yes,
Enrico. This is Suzuma. Look,
Yes.
just for confirmation, in the previous slide, what are you assuming for the injected proton spectrum? I mean, the spectrum at acceleration?
We took I don't remember exactly, it's 2.2 or 2.3.
Okay. So, and this is more or less reflected in what is seen in the when you say primary proton.
Yeah. I mean,
Okay.
Okay, does this answer? Okay.
Yeah. Okay. Thanks.
Okay, so we applied, as you can see, this model to the most well-known starburst, and as you can see, it pretty well described the multi-wavelength spectrum from radio to gamma rays in the case of MNT2, NGC253, and up to 20. Okay, so interestingly, in a recent study, we explored the ionization rate induced by cosmic ray in starburst. And first of all, I thought it was interesting to compare here what is the cosmic ray energy density of in starburst compared to what we have in the local interstellar medium as measured by Voyager and AMS. And as you can see, we have more than 3 orders of magnitude higher energy density in cosmic rays. And this has a strong impact in the, as I was mentioning, in the ionization rate induced by cosmic ray themselves, which is orders of magnitude higher than in our galaxy. And here we are showing some measurements in clouds of NGC253, and here is our prediction based in the based on our inferred cosmic ray distribution function. So maybe there is someone in the audience not muted, because sometimes I hear some noise. Okay, now it's gone. Okay, so interestingly, we are catching the good order of magnitude, but we are lying a factor 3 to 5 below the bulk of the data. And we haven't found a good explanation for that. But the possible causes of this are the following that we thought about it. So the first one could be the one-zone model limitation, namely that the cosmic ray energy density is not homogeneous in the starburst. So the clouds where it's measured might be closer to acceleration sites, so this might result in a higher cosmic ray-induced ionization rate, or this might be due to chemical model uncertainties or uncertainties in the parameters of gas mass and supernova rate in this environment. And the last very interesting and somehow more speculative possibility is that we can have MEV sources in starburst that we don't know yet and we haven't measured yet. But this could be a very interesting somehow thing to explore. Okay, now for people interested in the TV band, there are several open questions for Starburst Galaxies in the TV band. First of all, microphysics. So what I've discussed so far concerns the quasi-linear theory phenomenological assumption on diffusion. But there have been some studies suggesting that the high density of neutral could suppress the turbulence cascade from the injection length down to the smallest scale, and this would result in a phenomenological different transport where at low energy we have streaming instability, while only at higher energy we have namely beyond the TV range, we are having the standard quasi-linear theory on the turbulence injected at large scale. So this is interesting because it would have tremendous implications as far as neutrinos from starburst are concerned, because this would make the escape somehow more efficient. A second interesting topic that has been circling around in the last decade is that point-like sources such as pulsars or TV halos or ultraluminous X-ray sources could actually contaminate, into some extent, the highest energy domain observed by imaging Cherenkov telescope, such as HESS and Veritas. So there have been some claims that pulsar could work, and even myself, I'm on it right now. I'm trying to investigate whether this is possible and which could be the implication in terms of radio emission. Okay, this is not my expertise, but I found that it was interesting at least to mention that there have been some particle dark matter constraint imposed thanks to Starburst Galaxies, and I thought it was just nice to mention that Starburst could be used also for people studying new physics. So all these things that I just mentioned will be topic of a study of upcoming Cherenkov telescopes, such as the Astro Mini Array and the Cité that I'm showing here, left and right respectively. But let's not forget about our Chinese friends. They have currently operating the LASO telescope, and soon they will build also the LACT. And as far as galaxies such as M82 is concerned, so I estimated by eye that in an observational time of about a couple of years, we should be able to get the first measurement of M82 flux from an experiment such as LASO. Okay, this brings me to the second topic of this talk, which is the starburst wind. Again, let me remind you that the starburst wind is this kiloparsec side structure which is sustained and launched by the star-forming activity taking place in the starburst nuclear region. And in order to give you a quantitative understanding of this system, let me do a very simple math. So let's try to connect the star formation activity to the wind. So we have a star formation rate that I'm normalizing to 10 solar masses per year. Then we have a rate of supernovae that is associated to the star formation rate. So roughly one has a core collapse supernova every 100 newborn solar masses. So in the case of 10 solar masses per year, we expect one supernova per decade. And so that we can simply estimate the supernova injected power in the galaxy as 3 point something, or let's say something times 10 to 42 Earth per second. Now, we know from measurement that the mass loss rate is somehow strongly connected to the star formation rate through a parameter that is known as a mass loading factor, and which is typically in the range 0.1 to 1. And in this case, we would get for 10 solar masses per year, roughly 1 solar mass per year of outflow rate. So the typical speed that we measure for starburst wind in the hot component is of the order of a few thousandths kilometer per second. And the kinetic power that we get from the wind is of the order, again, of something times 10 to 42 Earth per second, which is more or less of the same order of magnitude of the supernova power. And indeed, since the 80s, we know that supernovae, the high rate of supernova explosion, is actually what is powering these large-scale outflows. Now, what about structure and evolution? So, as we know, since the 70s, steady winds develop bubble structure, and which have this onion-like feature characterized by an outer forward shock and the inner wind termination shock. And this is a standard outcome when you have a supersonic wide opening angle outflow. So just being supersonic, it creates the shock which expands in the external medium. Then we have the collision with the interstellar with external matter that is creating the innermost shock, the wind termination shock. And then we have the contact discontinuity, which is separating the hot shocked wind from the swept up material. So in terms of evolution, the system composed by two shocks and discontinuity expand with the constant velocity up to the swept up mass here becomes comparable with the total mass in the outflow itself. And when this happens, as in inelastic collision, we have that the system enters its deceleration. And during the deceleration, the wind termination shock decelerates faster than the forward shock. And this is why the bubble, namely the shocked wind region, inflates with time. So here it's somehow a zoom of one lobe of the M82 wind bubble structure. We explored it with colleagues in Paris through MHD numerical simulation. And here, respectively, on the left and right, I'm showing the behavior under different assumption of a regular magnetic field and thick or thin disk included in the simulation, the behavior of the termination shock and the forward shock. And as you can see, the self-similar scaling I was mentioning of the deceleration, that for the wind termination shock is 2/5, while for the forward shock is 3/5, are very good approximation at the first order of what we can expect to be the general behavior in realistic situations. So a second thing I would like to draw your attention to is the following. So we do not expect in general to have a strong shock jump condition at the forward shock, while we see that high Mach number is expected to be at the wind termination shock. So differently from supernovae, we do not expect the acceleration to take place here at the forward shock, but on the other hand, we expect it to be here at the wind termination shock. And this has a tremendous implication for acceleration of particles in this system, since the escape can only take place through the hot shocked region that is confining more efficiently, and cannot take place through the upstream, because here the advection is super strong and is pushing particles back to the wind termination shock. So here it's a sketch of that wind bubble, and for us, the system is characterized by the innermost fast cool wind launched by the Starburst nuclear region. Then we have the wind termination shock here and the hot shocked region, the contact discontinuity and the shocked external medium, and finally the forward shock. So we model particle acceleration and transport in this system in 3D, assuming spherical symmetry and a free escape boundary at the forward shock, where being a weak shock, we neglect any possible diffusive shock acceleration effect here. On the other hand, we take into account injection to take place here at the wind termination shock. And then we follow the transport in the whole system, accounting for advection, diffusion, and adiabatic energy losses and gains. As said, we measure the escape flux, assuming the forward shock as a as a free escape boundary, and we also account for particles interaction in the system through PP and possibly P gamma interaction. So this is how the solution looks like. So this is the spectrum as a function of a momentum or energy for this typical set of parameters, a mass loss rate of 10 solar masses per year, and a wind speed of a few thousand kilometers per second. And as you can see, the maximum energy is in the range of the hundreds of PV. And here in this plot, I'm showing on the x-axis the mass loss rate, here the wind speed. And as you can see, we have a wide region of this parameter space where the maximum energy is higher than tens of PV. So we have a multi-pevatron in starburst winds. And notice that here at low energy, the black line, namely the spectrum at the wind termination shock, is flat. And this means that we have a E2 minus 2, or if you want, P2 minus 4 slope as predicted by the diffusive shock acceleration. So here, what I'm showing now on the right is the radial distribution of particles in the system. So here is the wind termination shock location. Here is the forward shock where we have our free escape boundary. So all the particles are going to zero. And from red to blue, black and green, I'm showing the radial distribution increasing the energy. And the thing you can notice now, looking at the upstream region here, namely for radii below the 1, which is the shock termination shock location, is that low energy particles are forced to be attached to the shock, while the higher the energy, the more successful is somehow the backstreaming against the wind speed. And this is a natural implication of the competition between diffusion, which wants to homogenize particles in the system, and advection, which is pushing them back to the shock. And only particles at the highest energy can actually successfully get to closer to the center. And this is why here in this red and blue curve in the spectrum, I'm showing the spectrum at 75% and 50% of the wind termination shock, namely going inward. Only particles at the maximum energy are not suppressed, while we see a low cutoff, which is due to the fact that low energy particles are pushed by the advection to be attached to the shock. Now we can move our attention to the downstream region, namely R larger than 1, normalized R. And here we are assuming starburst wind bubble as energy conserving systems. So here the velocity profile is going down as 1 over R squared. Thereby, when diffusion is dominating, namely at low energy, the particle distribution is flat in radius, while when diffusion is dominated at the highest energy, we see a radial suppression in the numbers of particles. Okay, so here what I'm showing is the multi-messenger spectrum from a starburst galaxies like NGC 253. So here in green and dotted pink are the gamma rays and associated neutrino flux coming from the starburst nuclear region, where I did the assumption of maximum energy of 1 PV. And here in red and blue, I'm showing the gamma ray and the neutrino flux respectively from the wind. So first interesting thing is that here in the green line, namely the galactic disk or starburst nuclear region gamma rays, we have a suppression, and this is due to the gamma-gamma absorption we have in the disk, while this suppression is not taking place for the thick red curve, which is the curve, the gamma ray after EBL subtraction. This is before EBL, this thing red. You see that there is no suppression, and this is because we are far away from the galactic far infrared field. So detecting a flat gamma ray spectrum or gamma rays extending up to few tens of TeV might be a smoking gun of detection of particle acceleration and emission in the wind. And notice also that in the most pessimistic scenario, namely if in Starburst we weren't having multi-PV acceleration, that a substantial neutrino flux could come from the Starburst wind. Okay, now let's move to the last topic of this talk, which is the multi-messenger implication for the diffuse flux. So again, let me start reminding you that starbursts are interesting also because they were very numerous in the past of our universe, as I mentioned at the very beginning. And thanks to Herschel observation, we have the number of galaxies per unit co-moving volume as a function of the star formation rate for several redshift interval up to 4. So, and we developed a counting method for starburst requiring that the confining rate is more efficient than the escape rate. So in this way, we identified roughly twice the star formation of the Milky Way as a threshold for defining the minimum star formation rate of typical starburst. Okay, so here in this plot, I'm showing the multi-messenger diffuse flux. In red is the total gamma ray, while this dashed orange line is the direct component from starburst, and this in blue is the associated neutrino flux. And as you can see, starburst can provide a sizable contribution to both the Fermi-Lap diffuse flux and the ice cube neutrino flux. And of course, let me admit that this conclusion regarding the neutrino flux strongly depends on the maximum energy of accelerator in starburst. So if we had 10 or 100 PV accelerator, we would be happy and having a good contribution of starburst to the neutrino flux in this context, while if we were having only 1 PV at most accelerator, we would totally underpredict the neutrino flux. So this is an open issue. On the other hand, in the most pessimistic scenario, and here I'm converting this blue line in this green, so this is the neutrino flux, when at most PV accelerator are present in the starburst nuclear region. Here I added also the wind component. So, and as you can see, by adding the winds, we could still starburst could still contribute substantially to the ice cube diffuse neutrino flux, even in the most pessimistic scenario. So together with the gamma rays from starburst nucleus and starburst wind and neutrinos, we get also proton escaping from starburst winds. And here in this context, we computed what can be the contribution at Earth, neglecting the effect of intergalactic magnetic field. So that's also a point where this study can be improved. And here you see that the starburst wind escaping protons could saturate the light component of cosmic rays in the region between the knee and the ankle. So this is quite interesting for us because starburst might be one of the main protagonists, let's say, of the transition from galactic to extragalactic cosmic rays. Okay, so this is a broad view of the of all studies, of most of the studies that have been on starburst galaxy, multi-messenger flux and neutrinos and gamma rays in the last decade. And this is just to tell that there is not a perfect agreement with among all of them. So there are uncertainties in the way we count starburst, uncertainties in the transport. So we don't know whether the diffusion model we used are good or not, if there is ion neutral damping changing the diffusion, or there are so besides this, there are also astronomical uncertainties. So let's say that all the studies concerning gamma rays and neutrinos are predicting contamination from 1 to 100% in terms of gamma rays and neutrinos. So this is still an open question, and I would like to stress that this issue is not closed yet. Okay, as I mentioned at the very beginning, the Peretti Observatory is observing indication for anisotropy in the arrival direction of the highest energy cosmic ray with the sample of nearby starburst, and adding also the telescope array hotspot, this indication becomes even stronger. So here is a map of the excesses for the Peretti Observatory. Here you see a first excess. This is NGC 253 location. This is the Centaurus region where the starburst AGN NGC 4945 is present. And here in the hidden region, there is the telescope array hotspot where M82 is located. Here you can see here this bright part. So this is what we have so far, but of course also AGN catalog, even if they have somehow worst statistical significance than starburst, they are still considered as a promising candidate. They reached 3 sigma, while starburst are around 4. And this is a fun fact that I wanted just to show. Here we have the time evolution of the anisotropy of starburst and the Centaurus region over the recent time, the exposure of the Peretti Observatory, and here we see in the last couple of years, since 2019, a fall of the anisotropy in the arrival direction from starburst. So, and this is also the period in which I started publishing on starburst. So this might be just a coincidence, but I believe it's not, and there should be some conspiracy about it. And okay, besides this, if we take for good the indication that ultra energy cosmic rays might come from starburst, so in this Hillas plot, we see some ultra energy cosmic ray candidates, and here you see that starburst winds are also on the right spot in principle for ultra energy cosmic ray acceleration. So on the other hand, our model predicts just 10 to 17 electron volt as maximum energy for protons. This would somehow require, if starburst winds were the accelerators, that we would need something more to take place in the winds. So our model is predicting at least hundreds of PV protons, while for matching the Auger measurement, we would need one order of magnitude more. Maybe, we don't know, but it's possible that something else is happening in the wind. On the other hand, we might, since starbursts are the most active star-forming galaxies, it could be that these galaxies are the region, the environment where it's more likely to have a core collapse supernova and a long GRB occurring. So this correlation might be just natural consequences of a higher rate of gamma ray burst taking place in starburst galaxies. So we don't know about it, and this is still an interesting open question. To me, one of the most interesting. So an alternative scenario that got my interest and I really liked, because I think it's fascinating, is that James Matthews, Bell, and Taylor, and permutations of these authors propose that backflowing outflow in the jet of, for instance, Centaurus A or Fornax A could have the right condition for having ultra-high energy cosmic ray accelerator. And what we see as coming from the Council of Giants, as they define the nearby active galaxy, this might be just an echo or a reverberation of the release of ultra energy cosmic ray happened from the Centaurus A, which is in this sample of galaxies. So I think this is a very fascinating alternative that I thought it was good to mention. Okay, nevertheless, with some colleagues, we explored the impact and the consequences of having ultra-high energy cosmic rays injected in galaxies, in starburst galaxies, and here we, by assuming that ultra-high energy cosmic rays are there and injected in starburst environment, here we show. We have been able to provide a decent fit to the Auger measured ankle feature, and we also found out that having ultra-high energy in starburst environment would have important consequences for the neutrino flux measured by IceCube. So this is also quite interesting. So this leads to my take-home messages. So I hope I convinced you that star-forming galaxies are very interesting cosmic ray factories, and that starburst nuclei can approach calorimetric condition. So starburst winds can accelerate at least 100 PV protons, or petavolt if you want, in rigidity through the DSA, and possibly with some effects that we still don't know, might reach even higher energy. At least if we believe to Auger data. Then we expect gamma rays and neutrino both from starburst nuclei and starburst winds, and from all these systems we can get a sizable contribution to the multi-messenger diffuse flux. So new observatories such as the currently operating and upcoming TV telescopes will tell us new for sure about these galaxies. And regarding the ultra energy cosmic rays, the question is still open, and there is a lot of work to do on this topic. So I don't know how much time I have, so if I reached 45 minutes, I can conclude here. Otherwise, well, if someone is interested, I have some backups about NGC 1068, but maybe I see that it's quite late, so perhaps it's good to stop here, but feel free to ask anything also about 1068. Thank you.
Thank you, Enrico. Thank you very much.
Thanks.
That was great, very much. Very nice talk.
Thank you.
So yes, questions? Susuma, go ahead.
Yeah, thanks for the really nice overview. For M82 or NGC 258, nearby starburst, I don't think I've heard of clear observational evidence of the termination shock. Where do you expect that to be? And is it an issue that it hasn't been seen like in radio or X-rays, or do you expect it to be observable in the future, or?
So this is an interesting question. So I don't think that it's that easy to observe a termination shock there, given the low density we expect in the medium. So for starburst winds, we expect densities in the bubble to be of the order of somehow comparable to what you expect in the halo, from 10 to -1 to 10 to -3 particle per cubic centimeter. So I'm not that sure that it's easy to detect a termination shock. So I'm not sure of what could be the best tracer to observe that. But on the other hand, I would what I think it's somehow a closer termination shock, I think is the system Fermi bubble, Rosetta bubble. So if you even if the origin might be possibly different, might be a previous activity of Sagittarius A star, or possibly a past starburst activity, if you interpret the Rosetta bubble as thermal emission from a shocked wind, then the Fermi bubble might be the emission we see from electrons accelerated at the wind termination shock. So this is not fully answering your question, but this is all I got on this. Then if there is someone in the audience that know what could be the best tracer, I'm not sure it can be measured that easily,
Okay,
at
well,
least.
but I mean, certainly, I mean, it is of interest certainly for you and also for me. So yeah, hopefully, yeah, I don't know whether radio from emission from electrons might be observable. Well,
Yeah.
well, let's see.
I haven't mentioned the radio because this is my bad. So our model is for the moment only hadronic, because the method we use to solve the transport equation does not allow us to solve a fully calorimetric system, or at least a system where energy losses are dominant in some energy ranges. So I'm planning to extending that to make it fully numeric. And then I will have the leptonic prediction. So since I don't have any prediction, I didn't even consider the emission from electrons. But yeah, I absolutely agree, and perhaps this is a good direction to go. It's just I don't have any prediction ready in that sense.
Yeah. Okay. Thanks.
Thank you. Evgeny, you want to ask your question?
Thank you for the interesting talk. I have two questions. In one of your slides, close to the beginning, you have a correlation between the star formation rate and the luminosity of galaxies in gamma rays, I presume.
Yes, I can show this one, or if
you
want
the beginning.
The gamma ray one.
Gamma ray.
I think it's here. Gamma ray and ray.
Star formation rate.
Yes.
No, this one. I wonder what does it mean if you have star formation rate which is much less than 1 solar mass per year. Is it because you included very small dwarf galaxies, or you just extend the plot towards normal galaxies?
No, sorry. I don't know if you can see here.
It's a small Magellanic Cloud.
Yes,
okay.
yes.
So these are small galaxies. Yeah.
Absolutely, yes. So this is let's say all star-forming galaxies. So here the starburst domain is just here, from, if you wish, from a few solar masses per year to higher.
And another plot now closer to the end, where you have a plot of number of galaxies versus the star formation rate.
Yes. I know what you mean. I think it's this one.
Yeah, this one. I wonder if you look at the panel which is at the right.
Yes.
If you just try to integrate over the galaxies the star formation rate, what's the biggest contribution? Where is it?
Yeah, that's a very good question. I would say it's a good mix, but as far as I remember, the largest part of the contribution comes from the galaxy in the region or before the transition of the fall of the star formation rate function. So where they are numerous enough and somehow slightly more powerful than the minimum star formation rate that we have. So the luminosity, namely, is scaling with the star formation rate. So here are the most numerous, but here are the most abundant. So it's a convolution of the two. So, but if I remember correctly, are those immediately before the break of the Schechter function?
Thank you.
Thank you. Felix, hi, Felix. Go ahead, please.
I'm sorry, I had some problems with internet. So
I'm
now,
glad that you're here. Thank you.
Felix.
yeah, I'm just Enrico, my question is about this first calorimetry. Independent of any model, it's clear that we could estimate the density of cosmic rays. We don't need any model for that. And it's clear that density should be factor of 10 higher than in our galaxy, density of cosmic rays. So, but that could be organized in different ways. It is proportional to the injection rate and inverse proportional to the confinement time or diffusion coefficient, let's say, right? So what is so we have an upper limit for injection rate. We could put some 10%, for example, for the entire galaxy. So what would imply 10% or maximum possible injection rate for the speed of diffusion or confinement time? So from here, we could conclude it is calorimetry or not. For example, we could, if we would have power, you could increase power and then increase also confinement time. So the answer could be quite different. But for these galaxies, we are specific. We know what could be maximum injection. So what is the confinement time for the maximum injection?
I'm not sure to understand what you mean. So, okay, first of all, let's focus on the time scale.
How calculate the density of cosmic rays? It is, it depends on two parameters.
Yes, it's a supernova rate and then the dominant time scale.
Let's even don't discuss supernova rate, just general injection rate of cosmic rays. Cosmic rays, not just in general. It's what is 10 to 42, 10 to 43, 10 to 41 per second.
Yeah.
So nothing to do with supernova remnants. This is very general. Second one is confinement time. What now I'm saying, I mean, we could estimate quite safely maximum possible injection rate. And having this, and having density of cosmic rays, which comes purely from observations, of course, it's uncertainty about density of the gas. I'm just talking about hadronic part. I assume that these are hadronic. Then you could assume density of cosmic rays. So then we have a density of cosmic rays, then we have a maximum possible injection rate, then we should easy to estimate this the confinement time. So in other words, it should be only shorter than this possible one, right? Because we don't have any budget to increase injection rate. And I guess from here is coming that the conditions in cluster should be close to the Starburst Galaxy should be close to calorimetry.
Yes, in general, I would agree with your point, but so First of all, as far as the GV emission is concerned, yes. Then I also prefer the scenario, if you want, phenomenological diffusion scenario where we are having the quasi-linear theory. So
No, I don't like to have any theory. At this moment, what I want to say, we have a, let's say, luminosity of gamma rays above 1 TeV. Then it comes from the, it is, knowing the gas density in the specific volume, we immediately estimate the confinement time.
Yes, I understand your point, but so let's say that this is also my side as far as the TV emission is concerned. However, there are these two recent work that combine could let's say prove us wrong or offer a different interpretation of the flux only in the TV range, not in the GV. So GV is hadronic, dominated by the pion bump. But so if the cascade is the turbulence cascade is actually suppressed, and this would imply that cosmic rays start escaping around 100 GV or 1 TeV. So they would no, sorry, around in the TeV range, and so they would under predict the gamma ray emission. That in this context, one could.
You are moving to theory. I'm just before to moving to this microphysics. I think we could estimate the diffusion coefficient based on only gamma ray data and maximum possible by injection rate, which is possible in starburst galaxies. After having that, we could discuss should be, if we see this should be diffusion coefficient small, then you could discuss then should be higher turbulence, etc., cascades, etc. Not to start from the other side. That was I'm saying, because it's if it deviates, I mean, just it is clear that in starburst galaxies, cosmic ray density should be 10 times more. I don't need to have say that having any idea about diffusion. Actually, it could be also convection. I just need I have maximum rate, then I could estimate what should be my confinement time to get 10 times more the density than in our galaxy. And then after that, we could go and discuss how much you want about turbulence, about cascading, or all other things. But if you start with cascading, you can estimate the diffusion coefficient, and then you estimate after that, you get agreement, and you say, oh, disagrees, then it is a way, but it is a bit more complicated way, and that not straight way. I just, so again, there is often misunderstanding with these two things: total budget, cosmic rays, and injection rate, right?
Mm-hmm.
Because total budget is injection rate multiplied to the confinement time.
Yeah.
So total budget we get from gamma ray data and gas density, gas data, right?
In some, I mean, in some sense, yes, but I'm not sure. I would not bet my life on the origin of the TV emission. If there is a natural contamination from point like source, I'm not saying that this is the case, but
no, this is different story. But we are talking now about yes, that is. I agree.
No,
I mean, even the density could be 10 times less. Then forget about all these mechanisms, and these are coming. So I just want to say it's better to go a bit straight to have estimates. Let's assume these are cosmic rays, not point unresolved sources. If now we start to all these things, we'll make even more complex. But let's assume cosmic rays are producing gamma rays as you do here. You do here. You don't.
Yes, yes.
So that was you don't take any assumption about unresolved source contribution. So you assume that gamma rays are coming from the interaction of cosmic rays, and that is, gas density. So that is all. I mean, you do that the same. And then what I am saying only, I'm not criticizing your work. I'm just saying that it's very good, just from first principles, to have some numbers. And that is easy. That is very easy. And only after that to move to discuss what kind of turbulence is, how should be the calorimetry, or et cetera, It's clear that should be close to calorimetry, or 10%, maybe 5%. If I would have a source like AGN inside the galaxy, I could speculate and increase cosmic ray injection rate, acceleration injection rate up to 10 to 45 per second. Then I don't need any confinement, specific confinement. I mean, I could explain in a simple way. But in this case, yes, we have an upper limit on the injection rate because there is no budge source. That is my point, because I think when are mixing these things, immediately moving to the theory-oriented discussion on the diffusion, it makes a bit difficult. Otherwise, this is only was my point. Is just good to have this. Now, my second point is about multi-wavelength. So here is critical issue. What is the cutoff? 1 PV, 10 PV, 100 PV, as you said, that was, I don't think even with the termination wind, we could get more than 100 TV, right? Maybe 1,000 PV, but not much more, much beyond that, right? You had this plot I have. Okay, now, you see, here's very interesting issue now coming to multi-wavelength. You rightly saying about neutrinos, but neutrinos, as we know, always is difficult to detect. And there is another interesting point. You mentioned already, but very quickly. Secondary gamma rays, secondary synchrotron emission.
Okay, yes.
If you go now to 10 to 15, for typically 1 to 100 microgauss, you get X-rays. But if you go 10 to 17, it is square. You go even gamma ray domain. Now, and that is much better, resolution, at least in hard X-rays. Let's say 100 kV hard X-rays. And there is no competition much with other mechanisms, because there's no plasma, 100 kV plasma for thermal emission. And we know there is absolutely no effective radiation mechanism, non-thermal mechanism. So if we go to 100 kV, okay, there's a comment, it's not a question, sorry. So if 100 kV, having a good angular resolution, and these gamma rays are, these X-rays, synchrotron 100 kV, are produced immediately, almost on these scales. I mean, within 1,000 years, etc., in the same site. So they are parallelly are coming with neutrinos. Difference is only, or gamma rays, difference is only 1,000 years or less, actually less. So then we have not two neutral particles, neutral secondaries. We have the first secondary is hard X-rays. Not only hard X-rays, could be even 100 GeV gamma rays, but there, of course, there's a mixture. I'm saying that we good to try to find the interval where we don't have a big contribution from other mechanisms, other sources. And that is a hard X-ray. Hard X-rays, I mean really hard, 100 to 100 kV. And 100 to 100 kV, as I said, almost no way to have a plasma, such hot plasma. when we could speculate with, and well, binaries actually could go, of course, to that, but in general. And the non-thermal mechanisms, all are inefficient. All, absolutely all are inefficient. So that could be good at having angular resolution. That could be even better than gamma rays, direct gamma rays, except for this. So that could be very interesting approach, realistic to multi-wavelength. Of course, we could get multi-wavelength from radio, but this could be really connected. And then we could find, if we were lucky, there's the cutoff in the primary proton spectrum. And then we could say where they are coming from, the collective supernova remnants altogether, or the wind, etc. So I think it's good to a bit study this question more. Okay, I see even your curve. You see the Bremsstrahlung is just nothing, not big, and there's no mechanism. Actually, you have one mechanism, inverse Compton. I don't believe it. But we could discuss that later.
Yeah,
Yes,
absolutely.
because in order to produce hard X-rays, well, that is what is energy hard X-rays. You have your energies are still MeV. So yes, sorry.
So here is 100 kV.
Yeah, 100 kV. I cannot imagine how you get in 100 kV. So efficiencies, you produce 100 kV with relatively modest electrons. Very, very modest electrons, like Lorentz factor 100, and then cooling time is so long, the mechanism becomes very, so okay, anyway, that could be calculated carefully, but what I want to say is secondary X-rays, if we have a good instruments in hard X-rays, well, also even 10 kV, then that could be maybe a way to solve the problem. I think gamma rays are great. All we like very much gamma rays. Neutrinos are great. Some of us like very much neutrinos, but these secondary X-rays could be quite interesting first channel.
Oh, yeah, I totally agree.
For the 100 kV X-rays, there's no observation data, right?
Well, there's a
What are the observational data?
There are some upper limits on the diffuse from Chandra and New Star. Yeah, but
have data on all of these.
What about M82? With New Star? I mean,
the New Star data would be fantastic. I don't know if Julian is online.
So there was a proposal some years ago of a New Star observation of Starburst Galaxies, but and especially M82. But I don't know if there has been any update. At least when we published this paper in 2019, there was no update, and I saw some proposals, but nothing more on the IDS and around.
And then the connection with very high energy. Felix was asking, what is the highest energy? So the question is any news from LASO for these sources, for the northern ones at least?
No, not yet.
Is that expected? Is that surprising?
So it's so here I'm showing the LASO sensitivity curve. You should watch here at 10 TV. So here is the M82 infer flux at 10 TV. So here we are. This is 1 year LASO exposure. So we are a factor 3 or so. So 2 perhaps. So we need a couple of years more probably. But we are. I believe that we are not far from getting.
Could be better, Enrico, because these Cherenkov fluxes are. What are Cherenkov fluxes here? These 2 points are here. Where is Veritas his points?
Veritas does, right? M82, I think you have, but maybe, so there's some measurement from Veritas on M82.
This goes up to 10 TV, actually.
Has something on NGC 253, no?
Yep.
Yes.
So it'll be
but
good to see
NGC 253 is out of
LASO
is
can
right
see
on the horizon of
Yeah,
LASO.
exactly.
LASO will be able to spot M82, but I would say in the TV range we expect M82 to be the most luminous. Here you see around 10 TV, it's around 10 to minus 10 GV per centimeter square per second, while NGC 253 is slightly below. It's
Look,
around 5,
me-
10 to minus 11.
let's look at M82. I mean, that was LHAAS was fantastic sensitivity above 30 TV, and that is not much far from Veritas. So anyway,
Yeah.
so I could answer to your question. It's clear that if it will be flux, LHAAS could see immediately as a source, right? So that means the flux is not detected, at least obviously not very high to be like 5 sigma, etc. It is just guess, because it is, if you are looking on the sky, you'll have it, but it's coming anyway. So yeah, yes, this is very interesting question actually, is what is the spectrum? Spectrum, if you go E minus 2.2, 2.3 from Veritas, LHAAS should see that.
Well, not yet, because really here at around 10 TV, I don't think it had enough exposure time so far.
No. So what is that? 10 minus 13, right? 10
This is around 10 to minus 13 sorry, TV centimeter square per second.
curve.
And
Enrico, if you don't, your curve theoretical. If you just continue Veritas, extrapolate Veritas, then certainly LHAAS should see that. I mean, this is you are you are taking your theoretical curve, red one, right?
yeah, but how do you I mean, here you can draw an horizontal line, you can draw also
You cannot
a
that's my point. That is my point. You are saying, again, I think it's a bit we should not orient it on theoretical lines. I mean,
okay, let's look at the highest energy here, around the 5 TV. We are around 10 to minus 10, so it's 10 to minus 13 TV centimeter square per second.
yeah, if it's, but it's 2.2, right? Approximately. Veritas.
Yes.
So let's say if you go factor of 10, you decrease only slightly the flux, right?
Yes.
So it's anyway, what I want to say, it's very interesting. I mean, this is LHAAS is close to that, what Reshmi is asking. I mean, the first, it's clear that if LHAAS, it will be their signal, then it could be reported. So it's still below, and I imagine that is close to your red curve, in order to miss it.
Yeah, I think it's matter of time, but it's not if it's. I think it's when it will be detected. So I think it will come soon.
Yeah, it'll be interesting. So I'm afraid we have to stop here, Felix.
Simply say, just continue that.
Yes.
Already clear, they should be cut off somewhere, steepening above TV. So that means this cosmic rays Enrico was talking 10 to 16, 17, 18. So that LHAAS could give answer.
Yeah.
Absolutely, this is precisely what I was referring to here when I was talking about the wind emission. If LASO could tell us something about this, absolutely.
Yes.
We are emphasizing curves
yeah.
with neutrinos.
Yes.
Cameras are
We
just
will have to come back to this, Felix, because I have a hard cutoff. We have senior thesis presentations at Columbia. And I just wanted to say that we have a note from Kaya Mori on chat that we should come back to this topic. It's very interesting. Maybe if LASO has updates to discuss the X-ray observations of starburst galaxies. And so Kaya, we will get back to you as well on that.
That was my point.
Let's just thank Enrico one more time. Thank you very much. Very interesting.
Thank you.
Please send us the PDF so that we can upload it.
Absolutely,
and we'll also post the recording. And I would just like to request that the CDY chairs, if they could stay on, and as well as organizers of the CDY workshop, And
Yeah.
to everyone else, we will see you in 2 weeks for Oleg Kargaltsev's talk. Thank you.
Yeah.
Okay,
Okay.
bye-bye.
Thanks again.
Thank you very much.
Ciao, Enrico.
Ciao.